Okay, so find the Mclaurin series of e to the power of x. So we know the Mclaurin series is going to be, first of all, just plug in 0 here. So you're going to get 1. Then plug in 0 into the derivative. You're also going to get 1, right? The second derivative divided by 2 is going to give you half, right? So the nice thing about the function of e to the power of x is that when you differentiate it, it stays exactly the same. So you're going to get this. So the Taylor expansion, now you can imagine, is going to be the following. So instead of e to the power of x, we can approximate it with 1 plus x plus half x squared. So let's actually write it like this: x squared over 2, x cubed over 3, factorial, x4, 4 factorial. Pretty nice formula, right? So just remember, Taylor series is, the more we have this, the more we're getting close to e to the power of x. Right? So this is, right, the more we have these terms. So we follow the Taylor series expansion to get this as a representation of e to the power of x. But how do you know this actually is a representation? And we discussed how the Taylor expansion, right, plus remainder will form the function, right? Now, as n approaches to infinity, if the remainder actually happens to approach 0, that means I can say the function and the Taylor infinity are actually equal to each other. If this is not approaching 0, that means there's a difference between these two. You agree? Okay, so let's use this to show that it's actually approaching. Hopefully that it's going to approach 0. Okay, to finish off saying this is actually another way of looking at e to the power of x. So for us, this time for x, right? Let's say it's less than or equal to d. So let's set x equal to d. Then the m plus 1 derivative, right, which is just going to be e to the power of x, because it doesn't matter how many times you differentiate it, right? So if you plug in there the x value of d, we're going to get e to the power of d. Okay. So that means as x is between negative d and d, right, the m plus 1d is going to be between, it's going to always be less than, right, less than e to the power of d. Okay, so here you have it. So this is a constant. We don't need to worry about this. So let me just rewrite that as e to the power of d and the x n plus 1 over n plus 1 n factorial. N plus 1 factorial. Let's find the limit of this. Okay, we're interested in finding out what the limit of that is as n approaches to infinity. So let's figure out what the limit of that is. I think, so we proved this already. Do you remember how we proved this?
Oh, yeah.
So if you expand it, right, you get like x, or sorry, n factorial. So x n minus 1 all the way to 1 over n minus, right, all the to, right, so individually these guys are all approaching 0, right? So this whole thing's going to approach 0. We discussed this and proved this in an earlier section. So then from that, right, actually this is actually a pretty useful one to just have it remembered, so you don't need to sort of prove it again on the spot, right? So m factorial essentially always grows faster than the exponential function. Right? Exponential functions grow faster than power functions, polynomials. But m factorial is the king. It grows the fastest. Because this is growing a lot faster than the exponential, it's going to approach 0. You can think of it that way. So this is going to approach 0. So I have this limit here approaching 0, meaning um, as n approaches to infinity, we have Rn. Clearly, Rn, so Rnx, is, because its absolute value is greater than 0, right? And we also have it's less than or equal to 0. So by squeeze theorem, we've just shown that the remainder function of this Taylor expansion, right, of the e to the power of x is approaching 0. So this is the proof of this expansion here is equivalent to this infinite expansion is e to the power of x.